Right. Hello, everyone. I'm Ilias. I'm the technical lead for the Linaro Edge and Fog Networking department. And the reason of the presentation is the reference platform LEDs is offering, the architectural decisions behind the platform itself, why we did it, and how the platform is working, and the fact that we managed to use a generic kernel image across many ARM devices. So the first thing that we should do, and the easiest way to get this presentation going, is to try to describe what's the edge future, what are the edge platforms you're going to use, and how this is looking like, and what's the problems we're going to face. So on the cloud side, what people are usually used to is pick up commercial hardware, pick up your server, pick up a distro, or the distro of your preference, then install the distribution on your server, and go ahead and deploy it on your cloud installation. Now, the problem is that on the embedded side, each component at the moment is custom. So starting from the hardware, which is custom and soldered on the board, to the software stack, to the firmware components that you have, to your Linux distribution, or the operating system you're running, everything is customized. So these are two disjoint, fundamentally different approaches, and they address the very different market demands and needs. There's people considering that, when you're talking about edge, the first impression you get from people is that they think it's a scaled down cloud. So the idea is that we take whatever we do on the cloud, we shrink it down, and we have our installations and whatever we need. This is not entirely true. This is only true if you consider what edge is supposed to be and what edge is trying to describe. If you consider raw CPU power, or the amount of DRAM your server has, or how much storage you have available. If you take a step back and try to think about in pure numbers of devices and how many devices are going to be deployed in the field, eventually you'll figure out that the number of edge devices are bound to exponentially grow to the future. So they're going to scale a lot more than the current installations and the current deployments we have on data centers, and they're going to scale both in hardware diversity and software diversity. So as you understand, this is a completely different field from whatever we're used at the moment on our cloud installations. It should be obvious by now that the practices that we've been using for producing firmware, software images, and the whole software stack we need on embedded devices is not going to scale for the current edge needs. The common practice at the moment is that the vendor creates a BSP, you pick up the BSP, you compile your software, you compile your firmware implementation, you use that BSP as your basis, and then you boot your operating system and do the development of whatever applications you're trying to offer through your devices based on that BSP. This is not going to scale as the number of devices and the number of devices and the firmware and the hardware diversity grows, because you're going to end up with a huge number of BSPs and custom firmware and software implementations. Which leads us to what's actually LEDs. So LEDs is Linaro Edge and Fog Networking department, and I think the best way to describe it is try to read out verbatim the description we have on the website. So to fully realize the edge computing promise, a generic software stack shall rely on a standard interface with the firmware and hardware platforms. Those latter elements can remain highly customizable to efficiently address specific use cases. So although this means that your hardware might be customizable, you still need to standardize, to have a standard between the firmware and your hardware and the OS interface to be able to produce images that will fit multiple devices. So the Linaro members have joined LEDs to make this effort a reality, to make this hybrid approach a reality. And the way we figured we should do this is start by two major efforts. So the first one is the LEDs reference platform itself, and the reason of the presentation today. So the LEDs reference platform, what's trying to offer is, first of all, it offers a single image, a generic kernel image that's a single bootable single bootable image that you can run on any EBBR compliant board. Now, EBBR is the embedded based boot requirements from ARM, which are trying to describe the interactions of the firmware with the OS, and we'll get to that in detail further down the presentation. So the first one is the reference platform you're going to use for those hardware platforms. The second one is what we call trusted substrate, and it's a reference implementation of first of all, the EBBR spec from ARM. And in a broader sense, it's a subset of what ARM is trying to describe with the project Cassini. So in order to put everything we discussed up to now into a picture and give you a perspective on where the LED's reference platform is supposed to be deployed and what's its usage and what can you use it for. On your left-hand side, you have your really small embedded devices. You have your IoT sensors or your MCUs or really small devices that don't really need an enriched operating system. You don't need all the functionality that Linux offers, so you're better off using EmbeddOS or Zephyr or any RTOS that can be deployed on this kind of devices. And this is a custom firmware to OS interface. The LEDs doesn't try to address the standardization that's potentially needed there. If you move further up the stack, you have your smart cities, your cars, your servers, your small servers that are potentially deployed in 5G antennas or cameras or things that you're going to be using for smart devices and smart cities. Those do need an adaptable and certifiable firmware, because you need certification and you need some kind of standardization to move away from the current model of custom firmware interfaces and custom devices for every board. Finally, if you take a look further, this is where your cloud installations run. So this is where your big beefy servers runs, and this is standardized already. There's a well-known interface between the firmware and the OS, and as we open the talk with, you can just pick any hardware, pick a distro, an off-the-shelf distro that you prefer, and do the installation as is today. So the field that LEDs is trying to address and the operating system we're providing is trying to access is these middle grounds between the very small devices and the huge servers. So in order to do that, the first thing that you need to consider is that you need to standardize a bunch of things on the process. This is not yet another reference platform. This is trying to address a few problems that we've seen during the development and deployment of devices. So the first one is that there's a substantial fragmentation at the moment in the ecosystem, as it's regarding to the images that can be offered. So what happens right now, as we said, is that you get your BSP, you get your Yocto or a custom installation or a custom OS you get from the vendor, and this leads you to having separate images per board. This is even weirder, because you end up with different images per board, even if the boards are very similar to each other. So there are cases where you have pretty much identical hardware running different stacks. This eventually boils down to cost, because the more images you have to produce, the more images you have to test, the more engineering time you have to invest in producing and testing them, which means money. And those engineers would be better off developing applications that would make sense for you to sell on your customers or disrupt the industry, rather than trying to figure out how am I booting a new device and what's the firmware I'm putting in there. The second thing is security. Now, security is a complex issue, and it tends to be even more complex for edge devices. The reason it gets to be more complex is that on your typical cloud installations, you have a data center, right? So you have your servers physically protected from human access. You have someone protecting from changing the server. On the edge installations, on the other hand, you have no idea where this device is going to end up. It might be on a traffic light or on a 5G antenna or somewhere that eventually someone will get physical access. So the first problem is that the BSPs that vendors currently produce and offer, they're usually based on a kernel that's 2 years old, or that's the best case scenario. So we're not saying that by standardizing the firmware to the OS interface, we're magically going to run upstream kernels on every device and every problem is going to be solved. But one of the first issues that you have to address is how do you get from the bootloader stage, which initializes your hardware, up to your operating system in a standard way, so you won't have to rewrite it, and re-implement it for every new device. Another thing is that the engineering work you're putting into backporting various security fixes and very serious operating security fixes back into kernels is work that you could use otherwise, and this gets substantially harder as the age of the kernel gets older. So the older the kernel is, the harder it is for you to port security patches on your firmware and on your software stack. The second one is the technical debt that keeps increasing. So a huge percentage of the devices out there on the field nowadays can't even be upgraded. So upgrading is a challenge, and if it's possible, it's usually based on custom over-the-air update solutions, which in many cases is not even secure. So this just keeps adding up to your technical debt. It's not only the backports that you have to do, it's that you have to implement new firmware, implement a new software stack, test it, and as the number of devices grows, the hardware diversity grows, the more images you're going to produce. And it's not only the production of the images, it's also testing the image, providing Q&A for the image, providing help for the image, bug fixing, providing testing that the upgrades are going to work across versions of different hardware. So the technical debt you accumulate over the years keeps increasing, and there's nothing you can do about it. Oops, sorry. So let's have a look on how the platforms look today. So what's the description we just gave? How does it illustrate on current hardware, and how does it work on current hardware? So if you have three different boards, you have board A, board B, and board C. They each have a discrete bootloader, which makes sense because the bootloader's job is to initialize your hardware and make it run your operating system. But then if you take a step backwards and look the overall image, after the bootloader, you have three different kernels, three different root file systems with their respective applications and whatever you're going to offer. And these are fundamentally different between them. There's nothing that ties them together. So this is the multiple images that people have to maintain in order to have multiple devices on the field. So what we try to do on the platform, the first thing that made sense for the platform and use it as a basis to start was that we wanted this to be EBBR compliant. So EBBR is the embedded base boot requirements from ARM, which is trying to address the interoperability between SoCs, the hardware platforms, the firmware interactions and implementation, and the firmware operating system. So actually, if for platforms that host a vertically integrated stack, let's say your Yocto builds or your operating system or the Linux distribution you picked up, EBBR tries to minimize the engineering effort for the firmware to OS interface and the firmware to OS interaction. The second architectural decision we took is that we're going to use UEFI due to the EBBR compliance anyway. And we decided that we don't want any extra payload to be involved in our booting process. So what happens is that we boot the kernel directly as an EFI payload from our bootloader. We don't have grub in the middle. And this has a number of advantages. It has some disadvantages, but it leads to reduced boot times, which is in many cases on edge devices, and depending on the nature of the edge device, there's very strict boot time requirements. So getting rid any element of the boot chain that doesn't offer you any substantial functionality makes sense. It also reduces the complexity on the boot chain and on the software itself, because you have one less element to worry about. And it also reduces the pre-OS attack surface. And the pre-OS attack surface is something that starts to get interesting because we're seeing an increasing number of attacks against firmware. And the problem with the attacks against firmware is that they're fundamentally different from what people have been used to. So if you have a virus or an exploit, what you usually do is reinstall your operating system and wipe out the drive, and everything is fine. The exploit is gone. That's not the case with firmware. Those kind of attacks are designed to persist reboots, persist reinstalls. So the only thing you can do to get away from them is reinstall your whole firmware. So anything you can do to decrease the attack surface there is helping. The next thing is that we added SE Linux. Again, driven by security and focused on the security. We offer SE Linux on the platform by default. There's a problem with SE Linux and references platforms in general. You can't be too strict on the rules you're going to imply, because after all, you're offering a reference platform and you're trying to make people to use it and develop on it to get some ideas and drive them towards the direction you think that it's the correct one. So the problem is that you can't be too strict. The user has eventually has to choose the policies he needs, the restriction that he needs on SE Linux, and he has to make all the critical decisions about which resources do I allow access to and which I don't. But what we're trying to do is offer a sane basis that you can develop your policies on, and we offer all the tools that are out there to configure and run your policies on your software. The second one is that we offer a complete chain of trust. So using all of the infrastructure ARM offers, from the signature verification of the trusted firmware to the various payloads that you're running after that, like your secure operating system, which is Opti in our case, and then you verify your bootloader as well, which might be U-boot or EDK2. Depending on the implementation you choose. And from U-boot, we use the UEFI secure boot protocol to boot into our Linux kernel. So from the moment you press your button on the hardware and you press the power on button, you're reaching up to your Linux interface, making sure that each step you take towards booting Linux is exactly what the manufacturer aimed that to be. The next thing that we're offering is UEFI variable support and Opti coexistence. Now, this on the server world, this might not sound as too important, because I don't really know the needs of trusted applications in the server world. And what the servers traditionally do, at least the ARM servers, is that in order to store the UEFI variables, which are fundamental for the secure UEFI boot process, they use a dedicated hardware on the secure world. So you have a spine or a piece of hardware that can be accessed from the secure world only, where you install your critical UEFI variables. There's two problems there. The first one is that we believe that edge devices are going to need the presence of a secure operating system. The first use case that comes in mind, apart from trusted applications that you really need, you potentially have to run, is that the whole industry is trying to get an idea, and it's moving towards producing applications that take care of provisioning, of device onboarding, of all the critical pieces of how do I get my hardware to the field and deploy everything. This is supposed to be run on a secure operating system. So Opti, an existing operating system, is a must. And the problem with the current architecture, especially in EDK2, is that if you choose to have secure variables, secure UEFI variables in a secure flash, you can't have Opti running as well. This is a problem that exists today. So what we're doing on the reference platform, and we're actually upstreaming all the work in U-boot, EDK2, Opti, and all the projects that are involved, is that we managed to handle the variables via Opti. So your secure operating system is handling the variables, and we managed to store them on an RPMB, or a replay protected memory device, which is by design tamper-proof against rollback attacks and a various class of attacks. So we do have secure EFI variables on an RPMB device, and this is very important, because the number of devices that are starting to use to provide an RPMB is growing. So again, to put into picture, you press your button, you have ARM trusted firmware that starts up. And from the moment your ARM trusted firmware starts up, you verify your BL32 and BL33 workloads. The BL32 is the secure operating system you're running, which in our case is Opti. And from that point on, you verify your BL33, which is U-boot or Tianocore. The Tianocore is EDK2. And then it's U-boots or Tianocores trusted. Since you trust them, it's their responsibility to cryptographically verify the kernel signature and make sure that the operating system you're eventually booting is what your vendor was meant you to boot. So This is the full chain of trust on the hardware and the platform. Another reason why we decided on doing our own flat platform is that we needed fast feature adoption, so we couldn't rely on getting people to accept our patches and wait for the whole, procedure while we were trying to adopt new features. So, for example, one of the features we really wanted to adopt is that when you load your kernel, and nowadays in init from FS is pretty much essential for loading your operating system. There was the way of loading init from FS was tied to an architecture. So depending on the architecture you had, there was a different way for the kernel to load the init from FS, which wasn't what we actually needed. So there was an implementation and some features we contributed patches on U-boot and the kernel, and there's now an arc-agnostic way of loading the init from FS, and we use that on the LED's reference platform. The second thing is that due to the strong devotion we have on security, we wanted the TPM on the left reference platform. And since you don't always get a discrete TPM on your device, it's a hardware TPM. We took the decision of adding a firmware TPM. There's a firmware TPM stack from Microsoft, which actually works pretty well, and it's running under OptE. So you have your OptE running the firmware TPM part, and you have your TA on Linux doing the user space stuff you want. And we tend to use it for further security measurements like boot attestation, locking, remote attestation, and all the things you can do to protect your system using a TPM. The last thing is, since we did gain some focus on TSN, which is the time-sensitive networking used for industrial applications and applications that require very strict bounding latencies on the network. So we are on the kernels we compile, we add all of the tools you need on Linux and some libraries and some TSN related libraries like OPC UA that you might need to build your TSN applications. So after the overhaul we did, this is what the picture looks like. If you remember the first picture that we had, you had 3 boards, 3 different operating systems, and 3 bootloaders. Now, obviously, you still have 3 bootloaders because someone has to initialize your hardware for you. The difference is that this bootloader is now governed by UEFI. So you do whatever you have to do on your platform, but the way of how do you run your operating system after that has become standardized somehow. So you boot up your kernel, and what we did on the LED's reference platform is followed what ARM initially committed on the kernel and the principles the ARM32 and 64 bits were designed for. So you have your device tree, and from the device tree you can derive which hardware you need to initialize. You don't have to, you're not bound to having a single kernel for each device. You can have one kernel, and through the device tree descriptions, you can pick up your modules, initialize your hardware, add your vendor modules if you want, have a common root file system because that's always doable on the same architecture, and on top of that have the same applications. So by providing a more unified kernel, you can have a single distribution you can run on many boards as long as the lower layers are ABBR compliant. This is not, obviously this is not always good. For example, there are platforms that require very, very low boot times, and by doing this, you're increasing the size and you're increasing the boot size as well. But there's trade-offs here and there. So this will probably serve some of the use cases. Now, on the beginning, we talked about the LED's reference platform. We also talked about trusted substrate. So if you see the bigger picture, there's Project Cassini from ARM, which is trying to ensure that your now cloud native experience across a diverse and secure ecosystem is seamless. So you have your specification, you have the platform security architecture, you have your embedded based root requirements, the trusted based boot requirements, you have APIs and standards where ARM is implementing like Parsec, you have your device identity management, your device onboarding, and then you have your building blocks for that, which is the ARM trusted firmware. A secure operating system, OptE is there because we just happen to use OptE. You have your bootloaders, which need to be BBR compliant and support UEFI, and then you have your reference implementation of your operating system. Cassini is trying to extend the actual PSA edge infrastructures. And in collaboration with Parsec, which is trying to provide applications access to security services that are architecture independent, then you get a full secure reference platform that can also run secure payloads that are authenticated, and you can eventually trust what you're running. Now, regarding our future plans, everything is not perfect. We talked about security a lot. There's a problem right now. Your device security is as strong as its weakest link, right? So there are things that are not authenticated at the moment. For example, there's problems with device trees on the field. So, for example, if you pick up a device tree from U-boot, you usually can't boot Linux, and that works the other way around as well. If you pick your Linux DTB and compile U-boot with it, U-boot might not even boot up. And that device tree is not even authenticated or signed. So one of the directions we're working at is unified device trees that try to make a common interface across them and authenticate and verify the device tree that the device is actually using. Since you can't possibly imply device security without guaranteeing that the hardware description is what you bought, is what it's supposed to be. The second thing we're working on is AB partition updates for firmware, for firmware for starters, and eventually for the OS as well. Now, the AB partition upgrades have advantages that you can offer anti-bricking support, bricking protection, because it's when your device is deployed somewhere on the field, it doesn't make sense to send a technician over to flush it because the firmware upgrade failed. And due to the firmware attacks that we described before, preventing the firmware to roll back to a potentially flawed version that is open to attacks is also a must. The last thing is that we still, even with device tree authentication, we still have things on the kernel we'd like to attest for and authenticate. So we're trying to extend the Linux measurement, the integrity measurement architecture offered by the Linux kernel to verify as many files on the operating system as it would make sense to be secure. So, for example, the initROM-FS is one of them, since it's responsible for running your operating system. Now, how can you get involved? We have a first official release, which is based on 5.3 kernel. We don't officially build firmware snapshots, but in order to help people, we are building firmware files and daily snapshots for both U-boot and EBB and EDK2. Which enable the UEFI you want, and then we have our documentation on the Linaro GitHub that you can access, and the documentation describes how to build the platform from scratch if you want, or how to download the precompiled images and run it on QEMU. There's the number of platforms we support at the moment is not too vast. We support QEMU, we support an NXP device based on Cortex A72. We support 2TI devices, some ST devices as well. But the way we're compiling the kernel and the operating system, there's nothing that prevents the current distribution from running on more hardware. The only thing you have to do is make sure that your firmware can provide the EFI interfaces we're looking for. There's a bunch of devices already included in the kernel, and we're trying to add a bit more. That's all for the presentation. Thank you very much.